こんにちは。私の名前はクリスです。ここにいてよかった。Hi everyone. Welcome to this talk on lessons learned migrating the Maps SDK to Compose. I'm Chris, and I'm a developer relations engineer on the Android team working on Compose. Before joining the Android team, I was on the Maps team where I worked on a library called Maps Compose, which is a Compose interop library for the Maps SDK. I had a lot of lessons learned around Compose API design, and that's what I want to share with you today. But why am I talking about this, and why might it be relevant to you? When building UIs with Compose, you quickly realize that you end up building a library of components specific to your app, so you become a Compose library developer. So my hope is that the lessons that I will share with you will be relevant to the library of components that you are building. Compose was made stable in 2021, and a very common question that we receive is this: should I use views or Compose in my app? We want the question to become Compose only or Compose and views, where you should be doing most of your new development in Compose and only reaching for views in the limited cases where an advanced feature might not be supported. We believe Compose is the future, and view-based code will be seen as tech debt. If you went to Ben's talk on state of Jetpack Compose, this diagram should be familiar to you. The Maps SDK is a view-based library, so it falls under this path in the decision tree. To use the Maps SDK with Compose, you would have to use one of the available interop APIs to bring it into Compose. So what are those APIs? The Android view composable function allows you to bring a view into Compose. It accepts a factory lambda, which is called when the composable first enters the composition, and an update lambda, which is called when the view has been inflated, and for every subsequent recomposition, that update lambda would be re-invoked. Another option is to use Android view binding. This composable function requires view binding to be enabled in your app, and it enables you to inflate an XML view and bring it into Compose. To use Android view binding, you pass in a value for the factory lambda, where you would call inflate on the generated view binding class for your XML file. It also has an update block, which will be invoked when the view has been inflated and for every subsequent recomposition. Android view binding is the composable function that you want to use if you want to bring a fragment into Compose. It has specific fragment handling so that the fragment is removed when the composable function disposes and leaves the composition. Before Maps Compose was available, the most common integration with the Maps SDK in Compose is through using the Android view composable function. To use this, you would first construct a map view in the factory lambda, and then in the update lambda, you would call getMapAsync on the map view, which will asynchronously provide a handle to the Google Maps SDK object, which you can call methods on to change the appearance, such as adding markers, circles, overlays, and so on. In addition to this, the map view also requires that you invoke lifecycle methods on it when the corresponding lifecycle owner, which could be an activity or a fragment, undergoes lifecycle events. To do that, we can create a lifecycle event observer, which we can add as an observer to the current lifecycle. In the observer, we can then call the corresponding lifecycle event on the map view when a lifecycle event occurs. That code, this lifecycle event observer code, would be contained within a disposable effect composable function. This way we can listen to the onDispose callback, which would allow us to remove the observer from the lifecycle when the disposable leaves the composition. All that code can then be wrapped in a composable function. In the snippet, we're calling it MapViewContainer. And that composable function can accept parameters like the marker position that it then passes back down to the Maps SDK. What you end up having is essentially a wrapper around the Maps SDK. This is what developers had to do before Maps Compose was available. And depending on the integration and the needs on the map, it can take a couple hundred lines of code. And this is precisely the implementation that Crane had, one of the Compose sample apps that displays a map. It's a pretty simple use case where it displays a map with a single marker. But all in all, the code to write this was just over 100 lines of code. But what if you wanted to do more on the map, right? What if you wanted to display multiple markers on the map? So you can modify the composable function and take in a list instead. But what happens when it recomposes? You can either clear the map each time, which depending on how many times this recomposes might be acceptable, or better, you would have to remember the previous set of markers displayed, do a diff between the new set of markers and the previous one, and then based on the diff's result, you would either add markers, remove markers, update them, or delete them. And what if you wanted to do even more on the map, right? Like what if you wanted to add polylines, circles, polygons, and so on? So you would essentially have to repeat this pattern of remember the previous state, performing a diff, and performing actions based on the diff's result. But what about listeners? How about custom info windows, controlling the camera? How do you distinguish between moving and animating when moving the camera to a new position? What about setting properties on the map? So all in all, you developers essentially have to end up wrapping the entire Maps SDK surface area. And a lot of developers faced this issue. So it's not the best developer experience while using the Maps SDK. And ideally, this should all be handled for you. So wouldn't it be great if all that code was wrapped in a library so that you can use an idiomatic Compose version of Google Map? And that's exactly what Maps Compose is. It's an interop library for the Maps SDK. And it hides all the boilerplate code that I just showed so that you can add a map using a readily available composable function. So again, you don't have to write the code that I just showed. And Maps Compose is an open source library. You can see it at this short link, google/maps-compose. And yeah, go ahead and try it out. But let's do a walkthrough of what Maps Compose, what you can do with Maps Compose. So the simplest use case is to add a map with a single marker. To do that, you would call the Google Map composable function. And that function accepts a content lambda, wherein you can call the marker composable function to add a single marker on the map. Since marker is a composable function, you can use standard Kotlin syntax like for loops to add multiple markers on the map. To control the camera on the map, you can do so by creating a state-hoisted camera position state object, which you can create and remember using the remember camera position state method. In that method, you can pass the initial camera's position and then provide that as an argument to the Google Map composable function. So the camera position state object allows you to move the camera's position to another location by calling the move method. In the snippet, when the button is clicked, we perform a zoom out on the camera by calling a method on the camera update factory object, which we'll get to that in a second. So if you want a smoother camera transition, then you can call the animate method on the camera position state object. This method is a suspending function, so you need to make sure to call it within a coroutine scope. All right, that was a quick walkthrough of the features of Maps Compose. Now let's transition to the lessons I learned and how and why Maps Compose APIs were designed this way. So the first lesson is to think declaratively in Compose. This is perhaps the most important mental model shift when building UI with Compose versus views, and grasping this concept has implications in API design. As a quick refresher for how Compose works, thinking declaratively means that state entirely controls the UI. If you want to change the UI, you need to change the state first, which triggers recomposition, and then regenerates the UI. There's a really great page in our documentation about how to think declaratively in Compose, and I highly recommend that you read it to understand the different mental models of how to think about building UI in Compose. You can access it at this short link, google/thinking in Compose. So if thinking declaratively is what we want, what does it mean to not think declaratively? And a question that came up when Maps Compose was released was this: how can I call clear on the map? Since Maps Compose didn't expose a clear this API. So for context, what clear does is that if you call this on the Google Maps SDK object, it will remove all objects on the map. So it will remove all the markers, polylines, and so on. But in declarative thinking, if you want to clear the map, you have to recompose the map with state changes so that no Google Map child composable functions are invoked. So one way to clear the map is to wrap the Google Map content lambda around an if statement that's gated by a mutable state boolean. So when you change that boolean value, that recomposes the map, and then if it's true, then it will show all the contents of the map, and then if it's false, it'll clear the map. So that's how you clear the map in Compose. So one way this principle also translated in API design is through displaying markers. So again, I mentioned earlier that one way to handle displaying markers is that the Google Map composable function can accept a list of markers. And this is actually one of the earlier design iterations of Maps Compose. This is perfectly fine, though handling it this way has some implementation detail challenges, as I've mentioned, right? So you have to keep track of the previous state, perform a diff, and then add, remove, and update and delete as needed based on the diff's result. But if we think about this abstractly, the behavior of adding, removing, updating is precisely what Compose is excellent at doing. So the question is, can we model markers, adding markers to the map, in a more Compose-friendly way? And map and markers essentially have a parent-child relationship. So what if we create a familiar API that describes a child-parent relationship like contents in a row or column? And again, if we take a step back and think about what Compose is great at its core, it builds a UI tree over time, and it updates the properties of those nodes in the tree over time. And that's exactly the kind of tool we need here. So what if we can use Compose to build the tree of markers that we want on our map and have Compose handle updating the markers over time? So using Compose, Google Map can instead accept a composable function lambda, where the caller can then define what elements the map should display by calling composable functions like marker in the content lambda of Google Map. So instead of passing a list, we call composable functions inside the content lambda. And the advantage of doing this is that we can tell the framework what markers should be in and out of composition. So this is a lot more Compose idiomatic. We can use Kotlin control flow like loops and if-else conditionals. And we no longer have to remember the previous state and diff between recompositions. So Compose tracks all of that for us, which is really handy. To implement this child-based API, the marker composable function emits a compose node with a custom applier. The resulting implementation creates a new subcomposition that manages the map state instead of Compose UI nodes. To use a Compose node, you have to specify the type of the node. In this case, it's a marker node, as well as the type of the applier, which is a map applier in this case. So I'll talk about the applier in a second. A Compose node accepts a factory lambda, which will be invoked when the Compose node comes into composition. So when the marker composable function comes into composition, we want to add the marker to the map. So this is where we make the call to the Maps SDK Google Map object to add the marker on the map. And then the marker node is the containing class. So it's a type of node. In this case, it's a marker node that holds the marker instance. So apart from factory, it also accepts an update lambda. So this will be invoked when the marker composable function recomposes. So if, for example, the title of the marker changes, we can run specific code to ensure the underlying marker's title changes as well. So I'm only showing an example of title here, but this overall pattern applies to other properties as well. I mentioned that the Compose node requires that you specify an applier. An applier is an interface that receives tree-based operations that occur during a composition. So as the UI tree, on the underlying UI tree changes, if nodes are added, removed, or updated, you can listen to these events and perform their corresponding effect. So for markers, that means if the marker composable function leaves the composition, then we can listen to that event and remove the marker from the map. This design is used for other objects, not just marker, but for circle, polyline, and polygon, and so on. All right, so moving on to the second lesson, which is to reuse as much as possible. Ideally, using Maps Compose shouldn't be drastically different from the Maps SDK. So if you have used Maps SDK previously, it should feel familiar. And one way to do that is to reuse as much as possible while using, reuse as much classes and types in the Maps SDK while using Maps Compose. But of course, deviating when and where it makes sense. So one way that this principle manifested is by reusing the camera update class, which you create from a camera update factory. So internally, the library uses the same class, so why not repurpose this to perform camera updates on the map? So in the Maps SDK, how you would use camera updates is that you would call a method on camera update factory. So if you wanted to update the lat long and a zoom level, you can specify specific positions, and you can zoom in by 1 increment, or you can zoom to a specific zoom level. And then once you have your camera update object, you would pass that to move or animate on the Google Map object. So controlling the camera in Maps Compose is done through the camera position state object. And this is an object that can be hoisted and has controls like moving and animating the map. So in Maps Compose, this is how you would animate, or rather update the camera's position. Notice that the same camera update objects are used here. So this should be really familiar to folks who have used Maps SDK. And instead of passing it to the Google Map object, you would pass it to the camera position state object to move or animate the map. So notice that I said reuse as much as possible because there were some instances where reusing wasn't possible. So for example, the Maps SDK has this object or this class called a UI settings. With UI settings, you can update the UI on the map, like enabling zoom controls, enabling the blue My Location button, and so on. And you can't actually construct an instance of UI settings ahead of time. You have to wait until the Google Map object is constructed, and then you get a handle to it as a property on the map. So, but in Compose, right, going back to the first lesson, we want to be able to declare ahead of time what we want our UI settings to look. So since we can't construct an instance of UI settings, it's incompatible with the Compose way of doing things. So in this case, basically, the Maps Compose introduces a new type called Map UI Settings, which mirrors all the same properties in UI settings. So you would construct an instance of Map UI Settings and then provide it to the Google Map composable function to change different UI settings. So a related point to this is setting properties on the map. Google Map has a lot of properties you can set dynamically, like if building should be enabled on the map, if the My Location blue dot should be enabled, and so on. And a very early iteration of Maps Compose exposed these properties as basically as arguments to the Google Map composable function. But there were a lot of properties already, and you can imagine there might be more in the future. So it quickly became untenable, even with default values. So it really hurt the usability of the composable function. So there's really no optimal number of parameters to strive for, but in this case, we can reduce it and improve the usability by grouping related properties into a data class. And that's exactly what Maps Compose provides. So Maps Compose introduces a new class called Map Properties, which has all the same properties as the Google Maps SDK object. And the idea is that you would construct an instance of this and then provide it to the Google Map composable function. Moving on to the next lesson, which is to take advantage of Kotlin features. This one point might be obvious to you. Perhaps you're already very fluent in Kotlin, but I thought it'd be important to call out because there are a lot of libraries and apps that are written in Java, just like the Maps SDK. So thinking in Java is really different than thinking in Kotlin. And since Compose is entirely written in Kotlin, you should really lean into Kotlin features while developing your composable library. So some example of Kotlin features that are used quite frequently in Compose are extension functions, default parameters, lambdas, coroutines, and there are many more. So there's actually a great page on in our docs called Kotlin for Jetpack Compose, and this page outlines all the different special idioms that are commonplace in Compose. So these idioms are idioms that you should also use in your app or library. And you can check it out at this link, Google/Kotlin for Compose. So what Kotlin features does Maps Compose take advantage of? So Maps Compose, as you can see, or Google Map Composable, uses a lot of default arguments. So as a result, you can construct one without any arguments. It's not very useful. Or you can provide customizations like providing a modifier to configure the size of the map. Trailing lambdas are used for layouts in Compose. And layout is basically any composable function that accepts a composable function lambda as an argument. So layouts are expected to have a nice DSL syntax. And with trailing lambdas, you don't have to explicitly name the argument and include it within the function's parentheses. So to support trailing lambda syntax, it has to be the composable function lambda should be the last argument in the function. So as we've seen earlier, Maps Compose allows you to provide a trailing lambda so you could customize the way it looks. While you can still provide the content lambda argument as a function argument, it's preferred to use a trailing syntax. Coroutines are actively used throughout the Compose codebase to perform asynchronous operations. And Maps Compose uses coroutines for animating the camera, as we've seen earlier. So animating the camera is exposed as a suspending function, even though the underlying Maps SDK object implements camera animations as a callback-based API. So a good indicator of when you might want to use coroutines is anything async. So anything async that accepts callbacks, you can easily convert these to suspending functions. And suspending functions are really nice, especially when you have a sequence of asynchronous operations that you want to perform. So with suspending functions, your code reads much flatter. So it reads much like synchronous code. Whereas callback-based code, you would have to nest callback several times if you want to wait for different asynchronous operations to complete. All right, so the next lesson is to stay consistent with Compose Toolkit APIs. And what I mean by this is that it's good to strive by the same principles that the Compose Toolkit composable functions abide by. Inconsistency in API design can be quite frustrating, and it's a jarring experience, whereas consistency, on the other hand, is really pleasant, right? You don't even realize when something is consistent because it just works the way you expect it to. So these aren't hard and strict rules, but because there can always be exceptions, but you should strive for consistency for these reasons. So how do we stay consistent? One way is through vocabulary. So composable functions that return unit are uppercase Pascal case. So we say capital G Google Map and not lowercase g Google Map. The reason this naming convention was chosen is to re-emphasize that composable functions are declarative entities, so they follow the same naming rules for classes. Composable functions that return unit are also nouns. So we say simply Google Map and not a verb followed by a noun like render Google Map or show Google Map. Composable functions that don't return unit, so if they return something else, they should follow the normal Kotlin naming function conventions, so lowercase Pascal case. The one exception or special case of this rule is that if it remembers something, if the function is remembering information across recompositions, then we want to make that very explicit to the callee by adding remember as a prefix to the method. So we say remember camera position state and not anything else like create camera position state. Another way to stay consistent is to have predictable parameters. So every composable function should accept a modifier, and it should be the first optional parameter to enable customization. So this way, composables can take advantage of the rich set of modifiers available to sort of decorate and augment your composable. So since it's the first optional parameter, that means you can pass the modifier without explicitly naming the argument. Another way to be consistent is that if you're creating a layout that accepts a composable lambda, the parameter should be called content, and it should be the last parameter. As we've seen earlier, that enables the trailing lambda syntax. So yeah. Again, this is just a reiteration of earlier. It's preferred if you use a trailing lambda syntax for layouts. These are just some examples of how you can be more consistent with your APIs, and there's actually a great page on GitHub on Compose API guidelines. So this is an excellent resource for the library of composables that you're developing. It's something I extensively reference while building Maps Compose. So you can access it at this link, Google/Compose API guidelines. All right, the next and fifth lesson is to use Compose common types. Compose has a handful of types that might better represent a piece of data. So for example, the Maps SDK has an object called marker options. Marker options accepts or has a method called anchor where you provide two float values, basically an x and a y. And the anchor dictates the position of the map, the relative position of the map, of the marker relative to the position of the marker. So it defaults to the center, but you can configure this anchor by providing two float values. And Compose actually introduces a nice offset value class, which represents an XY offset in Cartesian space. So this has better semantics than two raw float values. So Maps Compose actually uses this offset value class for the anchor parameter. Another example of this is circle options. Circle options has two methods called fill color and stroke color, where you can change the color of the circle, and the color value that it accepts is an integer, a color int. Compose actually introduces a new data class, data holding class called color. So it's the same name as color in Android.graphics package, but it supports a lot more color spaces. You don't have to know too much about color, but why might this be relevant and why is it better to use the color class that's part of Compose is that if you're using material theming, then your colors can actually adapt automatically as the system appearance changes from light to dark mode. So that's a really nice advantage of that. So the last lesson I'd like to share, and I admit this might be very Maps Compose specific, is to provide an escape hatch. And what do I mean by that? The Google Maps SDK object is entirely managed by the Google Map composable function that's part of Maps Compose. So it handles mutating the map as state changes, right? So as state recomposes, Maps Compose will handle communicating those changes back to the Google Maps SDK object so that it's reflected accurately. So leaking this object can potentially have some side effects and unintended consequences, which is why the 1.0 version of Maps Compose, there was no way to obtain a reference to the Maps SDK object. But the Maps SDK actually has a companion library called a utility library. and the utility library provides certain features like marker clustering and heat maps. Maps Compose at the moment doesn't support these features, so it's desirable to essentially obtain a handle to that Google Maps SDK object so that it can be used with a utility library. So essentially that's what I mean by an escape hatch. There's a need for the Google Maps SDK object to escape from the Maps Compose library so that you can use it alongside the utility library or for any other use case you might have. So the escape hatch, you can use that by calling this composable function called map effect. And map effect will provide the Google Maps SDK object when it comes into composition. So you'll get a handle to that object and you can do whatever you want. You can use it alongside the utility library. You can add a marker, the old view-based way of adding a marker. Note though that this does require experimental, opting into this Maps Compose experimental API annotation because this is just an extra guardrail to prevent people from sort of making mistakes. And the idea is that in the future, this API would be removed because you should be able to cluster markers and draw heat maps in a native way. All right, so I want to talk next about limitations I ran into with Maps Compose. So Maps Compose, at its core, is an interop library for the view-based Maps SDK, and so there were some limitations that I came across. So the first limitation is that Google Map is not stateless, and a good litmus test for a stateless composable function is that the same state object should be able to control multiple composable functions. So in this snippet, I'm showing creating a camera position state object and passing it to two different Google Map composable functions. That is actually not allowed. This will error out. Although, ideally in a Compose native way, this pattern of having a single source of truth, the same state, controlling multiple UI elements, this should be allowed. But currently, because the Maps SDK Google Map object is stateful, it's not possible for this to work. So there's actually a one-to-one relationship between camera position state and Google Maps. So if you want to use multiple Google Maps in the same UI tree, then you have to have two separate camera position state objects. And the last limitation I ran into is that some properties on the map view or on the Google Map cannot trigger recomposition since they cannot be modified at runtime. So one example of this is if you want to provide a map ID to the Google Map, you actually you can do so by creating an instance of a Google Map options object and doing that within this Google Map options factory lambda. And the reason it's a lambda is because this will be invoked exactly once when the Google Map comes into composition. So, basically in Compose, right, everything changes, properties changing and state changing should trigger recomposition. But right now in Maps Compose, you can't change the map ID once it's set. If you want to change it, then you actually have to essentially put in a new composable function that replaces the map. So to summarize, think declaratively in Compose, reuse as much as possible, use Kotlin features, stay consistent with Compose Toolkit APIs, use Compose common types, and provide an escape hatch if needed. I wanted to link a couple of additional resources here for you to learn more. Again, here's a link to the Maps Compose GitHub page. Here's a link to our code labs. We have a bunch of code labs if you want to have a sort of a more hands-on approach to learning anything about Compose, anything from migration, from layouts to state to testing and so on. We also have samples. So I showed Crane, that was one sample app, but we have 7 or 8 different Compose sample apps that demonstrate best practices when developing apps with Compose. And then, of course, there's our documentation pages, which is a great resource to learn more. And with that, I'd like to send you off and say it's time to migrate to Compose. If you have any questions about this talk or any general questions about migrating to Compose or Compose in general, you can find me on Twitter at Arriola Chris. Thank you very much.